Hey guys, in today's lesson I want to go ahead and do a few problems on modeling situations with differential equations. And you'll probably get at least one question here on the AP exam regarding this. Okay, so I try to really create this one similar to what you guys would see on the test, and then just try to come up with my own scenarios. All right, it says the reading rate of a student R is inversely proportional to the square root of the time. And now if you remember differential equations, these are you're just kind of like your derivatives, rate of change. Okay, so it says the reading rate of a student R is inversely proportional to the square root. So inversely, that's important, proportional to the square root of the time. And it says write a differential equation describing the situation. Is the constant k positive or negative? So this is a telltale sign. It says the reading rate of a student R is inversely proportional. So right away it says reading rate of a student R. So that tells me dr dt, because it says reading rate, okay, is inversely proportional to the square root of the time. So whenever you're talking about proportion, remember there's always a k, a constant of proportionality. Now when it says inversely proportional, we're talking about the reciprocal or division. Inversely proportional to what? The square root of the time. So we're going to do square root of the time. Okay, and that's it. Now the last part, it says is the constant k positive or negative. Now think about this. If the more you read, the tired you get, correct? And if it's inversely proportional, you're slowing down, but the k is going to be negative. Okay, it's going to be negative. Why? Well, because think about it, you're getting tired, your reading rate slows down just because of your eye fatigue. And this would be the differential equation, and that's it. Let's try a second one. Something similar. A small rocket is launched from the ground and its position is given by the function s of t, where t is measured in seconds since the initial launch. During the first minute, the rocket's acceleration, okay, is proportional, okay, to the square root. There it is, proportional. The rocket's acceleration is proportional to the square root of the time since the launch. Write a differential equation describing the situation. Same thing, okay? So it's position, all right? Now, the position of the function is s of t, right? Okay, that's its position. But look at what it's telling me. During the first minute, the rocket's what? Acceleration. Okay, wait a minute. We started off with position. So what does that mean? Acceleration is the second derivative. Okay, the second derivative with respect to time. Okay, is proportional. There's that constant of proportionality, proportional to the square root of the time. So k, we always have that k, but notice it didn't say inversely proportional. It just said proportional. Okay, proportional. And we're going to get proportional to the square root of time. Okay, and that's it. So notice how we did that. Okay, even though it gives us the position, they're asking for what? The relationship with the acceleration, All right, notice that very quickly there. All right, and that's it. All right, and this one we're assuming that the constant is positive. All right. Next one. The growth, and this is a bit more in depth, it says the growth area of a certain bacteria is given by a differential equation. A, where A of t is measured, A of t is measured, it should be in square footage, and t is measured in hours. So let's look at it carefully. The area of the bacteria increases with respect to time. So you see this here? the area of the bacteria increases with respect to time. Right away, right there, it tells me dA dt. The area of the bacteria increases with respect to time at a rate directly proportional to the area. What does that mean? That means we have a constant directly proportional. There is my model right there. Okay, notice how we did that. So the first part is just logistics, and then here it's measured in square footage. Okay, the area of the bacteria increases with respect to time. Right here, dA dt, and at a rate directly proportional, K, to the area. At time t equals 5 hours, the area is 20 square feet. Okay, so at t, okay, at t equals 5, the area is 20 square feet. Okay, and is increasing, notice this, is increasing at a rate of 3 feet per second. Okay, so where am I going to put this 3? The 3 feet per hour, 3 feet per hour is going to go right here, dA dt. Okay, so that's going to go here. Okay, and then the area at that same time, okay, the area is what? 20 square feet. 20. Well, what about the 5 hours? Well, it's negligible. In this case, the time is negligible with respect to this rate of change, and that's okay. So now I'm going to solve it. So you end up with K is equal to 3 over 20. So what is my differential equation? Well, I go back here. dA dt is equal, now that I know my K, is 3 over 20 times A. And that's your differential equation, guys. Okay? But notice how I did that. The area of the bacteria increases with respect to time. Boom. Gives me my representation right here. Okay? Let's go ahead and do another one. Last one. It said the population of a certain bird is given by a differential equation where P of T is measured, is the number of birds in thousands, at time t, where t is measured in days. The population rate with respect to time, there it is again. Okay, so notice the population rate with respect to time is, okay, so let's write that one first. So the population rate dp dt with respect to time is directly proportional. Okay, so that means we have K, and I probably should have put directly proportional to the population, so it should be times P. In 7 days, there were an estimated 120,000 birds, and the population was increasing. Look at that. The population was increasing at a rate of 4,000 per day. So where do I put this for? Put it right here in dp dt. And then your K, I don't know. Your P, what's the population? 120,000. Okay. Again, this one, the time is negligible because we're talking about rate of change here. All right. So now we just solve. Okay, so that means K is going to equal to 4 over 120. Divide that by 4 is going to equal to 1/30. So, therefore, your equation, your differential equation is dp dt is equal to 1 over 30 times P. Okay? And that's what you want because look at the population of a certain bird is given by a differential equation. All right? This is my differential equation. This is a rate of change. So hopefully, guys, you kind of got the hang of it, seeing how we look at these problems. Really not that difficult. And let me know. I'll do more examples if you need them, but hopefully that helps. Till next time, guys.